Hello everybody, I hope you're all doing well. So we're going to be solving a problem on frames today, and here is a problem in front of you. So in this problem, you're going to be having three rigid bodies, okay? There is a bar DC, okay, so let me write that out. So there is a bar DC, okay, then there is a bar AC, which is an L-shaped bar, okay? L-shaped bar AC, and then a pulley, okay, and a pulley. Okay, these are all connected at the point C by means of a pin. Okay, so they are all connected at the point C by a pin. All right, so that's what is going on here, and there is a cable and a pulley arrangement that you can see, which is at the point C. And on the bar AC, there are lots of distributed loads acting. And what are the things that we are supposed to find in this problem? Okay, so let's do this. So find the following. Okay, the force exerted by the bar DC on the pin at C. Force exerted by bar DC on the pin at C. The second one I need to find is force exerted by the bar AC on the pin at C. Third thing, the force exerted by the pulley at C on the pin at C. Force exerted by the pulley at pin C on the pin. Okay, and then lastly, the support reactions at A and D. All right, so here is the problem once again. So I have this straight bar DC, okay, and then I have this L-shaped bar AC, and then I have this pulley. So these are three different things. These three different things are connected together at the pin C. Okay, there is a cable that is wrapped around the pulley, and this cable is fixed to the wall, and the bar DC is pin supported at the point D, and the bar AC is pin supported at the point A. Okay, so these are all pin supports, so you can make a note of that. That's a pin support. Sorry that the figure is a little crowded, but you get the idea. Okay, and of course this is also a pin support. Okay, so what is the strategy for these problems? Okay, I'm going to list down my strategy, my general strategy for solving problems on frames. Okay, so here is my overall strategy, and before you do that, recognize that you're going to have distributed loads all on this body, and usually we reduce the distributed load to a single equivalent force, and when we do that, the direction of the single equivalent force is the same as the intensity of the load distribution, and also the force magnitude is the area under the distributed curve, load distribution curve, and then the center of the force passes through the center of mass of the load distribution curve. Okay, these are three things that you typically understand. All right, so here is my strategy. So solution, and I want to go back to my regular color. All right, so the first step is reduce the distributed load to single equivalent forces. Okay, so reduce the distributed load to single equivalent forces. That is the first step. Then the second step is this: inspect the frame and see if you can find the support reactions by drawing the free body of the entire frame. Okay, so inspect the frame. To see if we can obtain the support reactions by drawing the free body diagram of the entire frame. Okay, if this is not possible, which means that I typically do this when the number of unknowns is equal to the number of equations, but if this is not possible, then what do? I have to dismantle the frame. Okay, if this is not a possibility, if this is not a useful exercise, then dismantle the frame. Okay, that's my second step. And my third step, an important step, once I dismantle the frame, then I inspect and see, do I need to draw the free body diagram at a point where the pins are attached? So upon dismantling, see if you need to draw the free body diagram at the pins connecting the different bodies. Okay, that is, do I need to draw the free body diagram of a pin? And what is the key idea here? The key idea, let me write that down. Okay, if only two members of a frame are connected at a free pin, I don't need to draw the free body diagram. Okay, so if only two members of a frame are connected at a free pin, then we do not need the pin free body diagram at that point. Okay, but if that is not the case, if more than two members are connected at a pin, or if the pin that the members are connected to is not a free pin, it has an external force or a support reaction, then you have to draw the free body diagram of the pin. Okay, but if more than two members of a frame are connected at a pin, connected at a free pin, or if two members of a frame are connected at a pin, and there is an external load or a support reaction at that pin, and there is an external force or support reaction at that pin, then we need the pin free body diagram. Okay, then we need the pin free body diagram. Alright, so in the second situation, we need to draw it. In the first case, we don't need to. Okay, so this is the important thing that you got to realize by inspecting. Okay, then this is the first situation where I don't need the pin-free body diagram. Alright, so in the previous problems that we had solved on frames, we had drawn the pin-free body diagram, but let us see what the situation is in this particular case. Alright. First thing is I'm going to take the distributed loads and then reduce them to single equivalent forces. Okay, so that's my first step. So let me do that here. Let me grab my figure. Okay, I'm going to get rid of some of these unnecessary things on the figure, of course. Let's clean it up a little bit. So I'm going to bring it down here. Okay, we already know that these are pin supports and so on, so we don't need a constant reminder. Alright, so cut that off, and I'm going to cut that off as well, and I don't need that. Okay, now I have a triangle distributed load, and on the bar AC I have a rectangular distributed load on the bar AC as well. Okay, so for each of them I'm going to replace them by single equivalent forces. Okay, so how do I do this? I first get rid of all of these forces. Let's see if I can clean up all of these guys inside here. So I'm just going to cut them all off. Okay, that ended up well. Okay, I'm going to cut that off as well, and hopefully that too. And likewise, I'm going to clean up all of these guys here, and you'll see in a minute as to what we are accomplishing. Okay, I'm going to clean that off as well, and I know that okay, the load distribution here was 1000 newtons per meter. Of course, I don't need the arrows anymore, okay, because I already know the direction of the equivalent force has to be in the same way as I have drawn these. Okay, and these load distributions will come back to them again in a second. All right, I just got to be careful here. All right, so I'm cutting it off, and then I'm going to draw these draw these as dotted lines. That's my next step. So I'm going to take all of these guys and then draw them as dotted lines, because they signify the fact that okay, there was a load distribution that was acting here, but I have gotten rid of it now, and I'm just replacing it by single equivalent forces. Alright, so first of all, let's start off from one thing and the other. I'm going to start with the force that is acting on the vertical portion of bar AC. Okay, look at this. The direction of this one was pointing to the right, which means I'm going to replace it by a single equivalent force. Okay, so that single equivalent force is also going to be pointing in the same direction. Okay, so I'm going to call that as a force FR1. Okay, then I will look at the and I will calculate these values very soon. Okay, then I'll look at the other force which is acting on the bottom portion here. The rectangular distributed load is acting down, so my equivalent force is going to be acting down. The triangular load distribution is acting up, so my equivalent force is going to be acting up. Okay, so I'm just going to draw that out here. I'm going to call it as FR2. Okay, and then I'm going to draw this up here, and I'm going to be calling that as FR3. Okay, so what is FR1, FR2, and FR3? Okay, so FR1 is going to be the area under the load distribution curve. So this is going to be half times the base times the height. So the base is 0.3 times the load intensity. The load intensity for each of them was 1000 newtons per meter. As you can see, the largest load intensity of the triangle is given to you, 1000 newtons per meter. This is 1000 newtons per meter. Likewise, the largest intensity here is 1000 newtons per meter. So area of the triangle, half times base times height. Half times the height, which is 1000, times the base, which is 0.3. Okay, so same story. So half times base times height. Okay, so FR1 is going to be equal to 150 newtons. Then FR2 is going to be half times base times height. Well, this is a rectangle, so just length times width. So this is going to be 0.6 times 1000, which is going to be 600 newtons. Okay, and then FR3 is going to be half times the base times the height. The base is 0.6 and the height is 1000. Okay, so all put together this is going to give me 300 newtons. Okay, so these are the forces that are acting here. Now where do they act? Okay, so I'm going to get rid of all of these. So cut that off, and we already know what these are. Okay, so I'm just going to leave that there. If I have a triangle distributed load or a rectangle distributed load, then the location of the force either way is going to be at the geometric center of the body. And for a triangle distributed load, we know that that is going to be at a height of 2/3 the total length, where the geometric center is located, which we have seen in our problems on distributed loading a while ago. Okay, so this is going to be 2 times by 3 times the total height, which is 0.3. So this is going to be 0.2 meters, which means that this is going to be 0.1 meter. For the rectangle distributed loading, that is a fairly trivial procedure, okay, because it is just going to be halfway down the total. So that's going to be at a distance of 0.3 meters from each side, okay, as you can see. So I'm just going to break this up into 2 pieces, and let me draw one more line here. Okay, so this is going to be 0.3 and then 0.3, because that's going to be half of what the total length of the rectangle is. And then for the triangle distributed loading, once again here, okay, from the pointed end of the triangle, this is going to be at a distance of 2/3 the total length of the triangle, or the total base length of this triangle in this case. Okay, so that's going to be 2/3 of 0.6. Okay, so which is going to be 0.4 meters. Okay, which means that this length here is going to be 0.2 meters, because the total length is 0.6. All right, now we have broken the force into its component, into its we have replaced the distributed force, I'm sorry, by its single equivalent forces, and we have also marked where these are acting. Okay, something that you want to keep a very brief note on. Okay, triangle load, okay, so acts at a length of 2/3 L from the pointed end. Okay, that's typically what I have mentioned. And for a rectangle load, it's L by 2 from either side. Okay, that's I guess we don't need to state that, it's quite obvious. All right, so then I grab this figure, which is a little more cleaned up figure here, and of course these are supposed to be in dotted lines, so let me very quickly do that. I need these dimensions again at some point, as you will know. Okay, I'm probably wasting my time doing this, but let me just try it at least one more time. Okay, all right, that's good enough for me. Okay, so we have all the dimensions done. I'm just going to grab this figure here. Now this is a little more cleaned up. Okay, so I'm going to copy that, and I'm going to bring that down here, and I'm going to clean it up a little more by saying, okay, I know that I have done all these calculations, so I'm going to get rid of them. Okay, so cut them off and then say, okay, this is 0.2, 0.3, and 0.3, and of course I know that as well, and then come and put this here. All right, fantastic. And I know the magnitude of all of these. FR1 was 150 newtons. Okay, so maybe let's write this down. So this was 150 newtons. FR2 was 600 newtons, and FR3 was 300 newtons. Okay. All right. Just want to make sure everything is fine. Okay, so then I come here and then look at what I have to do next. I inspect the entire frame. Now when I look at the entire frame, there is a pin at the point A, there is a pin at the point D. If I had to draw the free body diagram of the entire frame, I would end up with having four unknowns but only three equations of equilibrium, so this is not a good idea. Okay, so which means that I have no other option but to dismantle the entire frame. Alright, so I'm going to write this down. So if I look at the free body diagram of the entire frame, I haven't drawn the free body diagram. You see, I'm just inspecting the frame. I don't want to waste my time by drawing the free body diagram and then discovering later on that, hey, I have more unknowns than equations, so I'm not going to go anywhere good, you know. So that's my philosophy here. So I inspect the frame. Okay, there is a pin at the point D, there is a pin at the point A. Okay, so pin at D, which means that two unknown reactions. Then there is a pin at A. Two unknown reactions. Okay, but I have so a total of four unknown reactions. So if I draw the free body diagram of entire frame, four unknown reactions. Okay, two at A and two at D. Okay, but then the total number of equations of equilibrium is only three. The number of equations available only three. Okay, so which obviously means that it will be better to dismantle the frame. Okay, and so since the number of unknowns is more than the number of equations, number of equations for the full FBD of the frame. Okay, we try to draw or dismantle the entire frame. Okay, or draw the free body diagram of each of the bars of the frame. That's what I was planning to write, but dismantling it is easier to write, so let me do that. So dismantle the frame. Alright, so that's the conclusion that I have come to by looking at this particular problem. Alright, so what do I do after dismantling it into its individual members or into its individual parts? Now I go back to the frame and I look at it. Okay, at the pin at C, where there are three members of a frame connected, do I need a pin free body diagram? I obviously do, right? Because I have mentioned earlier that when do we not need a pin free body diagram? Look at this. If only two members of a frame are connected at a free pin meaning that a pin where there are no support reactions or external forces acting, then I don't need a pin free body diagram. But if more than two members of a frame are connected at a free pin, for example, the pin C is a free pin because there are no forces acting directly on the pin at C, and there are also no support reactions at that point. It is just the forces due to the individual bars connected at that point. Or if I have other situations where I have two members at a frame, but then I have external forces and support reactions at that particular pin on the frame. Okay, then I have to draw the pin free body diagram. So I am looking at this first situation where I have more than two members of a frame connected at a free pin. Okay, so then I have to draw the pin free body diagram. Okay, so here is what I do. I take this entire frame which I have cleaned up and written down here, and then I break it up into three pieces: the bar DC, the bar AC, the pulley, and the pin at C. That will be the fourth piece. Okay, so here is what I'm going to be doing. I'm going to be writing this down. Okay, so look at pin C. Okay, there are more than two members of a frame connected at that pin. Which means we need to draw a separate free body diagram of that pin. Okay. All right. So what I'm going to do is I'm going to look at each of these bars. So let me bring this figure once again. I'm just carrying it wherever I go. It's like my safe blanket or something like that. Okay, so I bring it down here. Okay, and then I say, okay, hey, what are the parts of the frame? I have the bar DC, so I'm just going to copy that and I'm going to paste it down here. Okay, so this is the bar DC, easy peasy. Okay, then I have this bar AC, so I have to grab a lot of these things. So I'm going to grab all of these guys on the bar AC. Okay, and I'm going to copy that and I'm going to paste it down here. Okay, so this is the bar AC. And then I have the pulley, which I'm going to grab from here in a second. Okay, so what do? I cut the pulley off. Okay, so I cut the cable off that holds the pulley. So if I cut the cable off, okay, that's essentially what I'm doing. If I cut it off, then I know that there is a little bit of the cable that is sticking out from the pulley, so which means that I have to grab all of these little pieces. Okay, so I copy that, then I bring it down here. Okay, cut that off, and of course I also have a pin at the point C, right? So if you want, you can actually draw this pin at the point C. So I can, let me do the following. Okay, let me just paste it down here. Well, I don't need to paste it down here. I just want to show you that there is actually a pin at that particular point C. So maybe I should have shown it this way. Now maybe let me do the same thing on the other figures as well. A little more forethought would have been useful, right? That's usually what happens when you do things in a hurry. Let me also mark the pin right down here. Okay, and of course there are pins connected here as well, but these pins are connected to the wall, as you know. Okay, and of course here too. Okay, so now we are good to go, and I also have to draw the pin free body diagram. Okay, so somehow I need to bring that down here as well. So pin free body diagram at the point C. I need to make some space for that. So I'm going to capture all of these guys and I'm just going to write it out here. So I'm going to draw the free body diagram of bar DC. So a bar DC, then this is the pulley and cable. Okay, then this is the bar AC, and then this is the pin at C. Okay, so these are the free body diagrams that I'm going to be drawing, and I have a good amount of work to do, so let's get on it. Okay, and this is the bar AC. First of all, since I cut off the cable at the pulley, I know that this is the same cable, which means that the tension on this portion of the cable is also going to be 1000 newtons. Okay, then I say, okay, hey, there was a pin acting at the point C on this pulley, which means I'm going to have pin forces, which I'm going to call as CX and CY. Okay, these are the forces exerted by the pin on the pulley, which means the pulley is going to exert equal and opposite forces back on the pin, which means I'm going to draw them as CY and CX in the opposite direction. Okay, so this is going to be CY, and then I'm going to have a CX in the opposite direction on the pin at C. Okay, this is the situation so far. Then I come to the bar DC. On the bar DC, I see that, okay, hey, there was a pin acting at the point C. So I'm just going to say, okay, this is going to be some force CY and some force CX, but I don't know if this force CX and CY is the same as the CX and CY on the pulley, so I call it as a CY prime and a CX prime. Okay, and then I put equal and opposite forces back on the pin. Okay, this is the force exerted by the pin on the bar, which means that this is going to be CY prime and CX prime back on the pin. This is CY prime, this is CX prime. Of course, I'm going to have a force DX and DY as well. Okay, It doesn't matter what the direction of your forces are. I'm just assuming them to be in some arbitrary direction, as you can see. Okay, and then I come to the bar AC. I'm just going to scoot this over so that I have some space, hopefully. Alright, then this is the bar AC. Here is the point A. At the point A, I'm going to have some pin reaction, right, as you know, because this is connected by means of a pin support. Okay, so I'm going to call them as AX and AY. Okay, so this is going to be some force AX, and then I'm going to have a force AY which is acting vertically up. These are all, once again, arbitrarily chosen directions, as you know. Okay, then what else do I have? I have the pin at C. On the point C, there is a force exerted by the pin at C on the bar AC, so I'm going to call that as a CX and a CY. But hang on a minute, I call this as CX and CY, but there is no guarantee that this CX and CY is the same as the CX and CY on the pulley. Further, I don't know if this is the same CX and CY as the CX and CY prime on the bar DC, so I'm just going to call it by a different name, a double prime. Which means that back on the pin, there's going to be a set of equal and opposite forces. Okay, so this is going to be in the following direction. So let me just make some room for myself here. And I'm going to bring these figures once again down here. So this is going to be a CX double prime. Okay, and a CY double prime, which is going to be acting vertically up. Okay, and this is going to be a CY double prime, which is going to be acting vertically up. Okay, and the CY, as you see here, goes with the red color. So each of these pin forces go with the particular color that I have used. Okay, so let me just mark a little bit of red here so as to show that as CX. Okay, I hope this is clear to everybody. And here is CY prime and CX prime. Okay, so these are my free body diagrams as such I have drawn here. And of course I have some dimensions that I have to finish off labeling. Okay, distance from pin C to where the end of the triangle distributed load. That one, if I go back to my original figure, right, the total length is 0.6. This is at a distance of 0.3. So a distance from the end of this line here, okay, all the way to the pin at C is going to be 0.3 meters. So I'm just going to draw that down here. Okay, so this is going to be 0.3 meters all the way from here down and down to where the other forces are acting, down to these other dimensions. And once again, I'm trying to draw straight lines, but you know, my struggle with them. 0.3 meters. All right. Okay. So what are these forces? So I'm just going to list them down here one by one. I'm going to bring these figures down to the next page. Okay, because I don't want to clutter it all up here. So I'm going to copy all of that. And I'm going to bring that down here. And I'm going to make a couple of statements before we proceed ahead. Okay. So I'm going to copy that. And I'm going to bring that down here. Okay. So what are the things I'm going to write down? If I look at CX and CY double primes, okay, or CX and CY. So these are the forces of action and reaction between the pulley and the pin at C. Between the pulley and the pin at C. Okay, forces of action and reaction. Let me scoot this guy up a little down further. Okay, that should be good. And then I look at the next one. Okay, so CX prime, CY double prime. These are forces of action and reaction between the bar DC and the pin C, as you can see. Okay, and then lastly CX double prime, CY double prime. These are the forces of action reaction between the bar AC and the pin C. Okay, so these are the three things that I have marked on my pin free body diagram and also on the respective bars here. And the whole idea is, okay, how am I going to find all of these out? Okay, so let me start off, and this is not a minus here, I'm sorry, this is 1000 newtons once again here. Okay, this is 1000, and of course I know that this is also 1000, so they're all the same, they're all in equilibrium. Okay, each and every one is in a state of equilibrium. And typically for me, the easiest one to handle are pulleys. So I'm going to grab the pulley, look at the free body diagram of the pulley. I'm just going to copy that and bring it down here. So I'm going to just start attacking them one by one. I'm going to say sum of all the forces in the x direction is 0, forces pointing this way. So I get Cx is equal to 1000 newtons. And then I sum forces in the y direction, and I set them equal to 0, and I say, okay, hey, Cy is also 1000 newtons. So I'm done with finding Cx and Cy. Okay, that was easy. Okay, so that's the first thing I look at. The second thing I look at, I just look at the problem. Okay, what seems easy to look at? In the first situation, the pulley was very easy to look at because it didn't look like there was much happening. Then this bar DC, that looks like a good creature to attack as well. So let's take that bar DC, because AC, you see lots of things are going on AC. I don't want to touch that. If I look at the pin, looks like I have like hundreds of forces acting on the pin, so I don't want to touch that pin either. So I'm just going by my gut feeling and saying, okay, hey, let me look at the easy pieces first, then let me look at the harder ones. Okay, so then I go to the next situation. I draw the free body diagram of bar DC. This is one of the obvious questions that I would be asking if we were an in-person class. What is the bar DC called? It should be very obvious to you that the bar DC is a two-force member. Okay, there are forces at only 2 points on DC, which means that DC is a two-force member. Okay, and since DC is a two-force member, the force has to be along the line joining D and C. Okay, so which means that the force along DC has to be along the line joining D and C, which implies that dx should be equal to Cx prime should be equal to force FDC, and dy should be equal to Cy prime, and that should be equal to 0, because I shouldn't be having a force there. And if you are in doubt, okay, if you're in doubt and say, okay, hey, how do I know that dy and Cy prime are 0? Here is what you can do. You don't need to do this. If you already recognize this to be a two-force member, if I call this distance as, I don't know, I think it's 1.2 meters here, I could sum moments about the point D. Okay, so if you don't want to do this, okay, you can say that, okay, sum of moments about the point D is equal to 0, and then I say counterclockwise rotations are positive, so this is Cy prime times 1.2 counterclockwise, that's equal to 0, which implies that Cy prime is equal to 0, which means that Cy prime is equal to minus dy should also be equal to 0. Okay, this is the reason why that is the case. Okay, so I get a really good news here. Okay, so this implies that from the bar DC, I figure out that Cx prime is equal to some force FDC, and then Cy prime is equal to 0. Of course, I don't know what that force FDC is, but I'm still in a much better place than before. Okay, so what do? Then I look at my options. I've handled the pulley, I've handled the bar DC. I know sufficiently enough number of forces which are acting on the pin at C, so let me go ahead and look at that. Okay, so because I still can't go to the bar AC because I have 1, 2, 3, 4 unknowns there. AX, AY, Cy prime and Cx double prime, Cy double prime and Cx double prime. So I have 4 unknowns on the bar AC, so I still cannot go there. So I'm going to look at the pin at C. Okay, draw the pin free body diagram or take this diagram and then start working your magic on that. Okay, so I'm going to go to the third part of the problem. Okay, all I do is I have to sum forces up. Okay, sum of forces in the x direction. What are the forces in the x direction? Things pointing to the right are positive, things pointing to the left are negative. So I'm going to have cx plus cx double prime is equal to, or minus cx prime is equal to 0. I already know cx. We know cx from before. Okay, this was at the pulley, right? Cx was 1000 newtons. Okay, so this is 1000 newtons, and then cx prime, I had written it as FDC. I just want to write my cx prime was FDC, which means that I now have cx double prime is equal to, and just substituting, so this is going to be FDC minus 1000. Okay, so that's something that I will write down. Then I sum forces in the y direction on the pin, set them equal to 0. Okay, what are the forces in the y direction? I'm going to have cy double prime pointing up. Okay, then cy prime and cy pointing down. But I already know cy is equal to 1000 newtons. Alright, how do I know that? I know that from the pulley. And I also further know that cy prime is 0 from the bar DC, because DC is a two force member. Okay, so cy prime is equal to 0, which implies that I know that cy double prime should be equal to cy plus cy prime, which means that cy double prime is equal to 1000 newtons. This is beautiful. So I have actually found out one of the unknowns from the bar AC this way. Okay, so I have so far what are the things I have? So Cx is 1000 newtons, Cy is 1000 newtons, Cx prime is sum for FDC, Cx double prime, or Cy prime, let me write Cy prime, its counterpart, Cy prime is 0, Cx double prime is FDC minus 1000, and Cy double prime is equal to 1000 newtons. So these are the things that I have so far. Okay, now I'm ready to tackle the bar AC. Okay, there is not much for me to do there. I just have to sum forces up and some moments up. So let me go to the bar AC. Let me grab that figure from here. Okay, so here is my figure for bar AC. So copy that and bring it down here. So this is the last thing I'm looking at. Okay, so this is now the free body diagram of AC. Okay, so here I had looked at the pin at C. Then here this was the bar DC, and then here that was the pulley. Alright, so these are the things that we looked at individually. Okay, and then each piece is in a state of static equilibrium. This is the basic idea in statics, right? That's a good thing. And so by looking at each piece, I can kind of figure out, okay, hey, how are things happening here? Okay, and in this figure I already know that Cy double prime is equal to 1000 newtons. Okay, and how do I know that? I just calculated it here. Okay, all right, so if I know Cy double prime, then I obviously can start summing forces up in the y direction and find out the force Ay, and I can sum moments and so on. So let me sum moments at the point A. Okay, so sum of moments at the point A is equal to 0. So this is my first move in this particular problem. Look at this. So this is going to be, first of all, start from the forces on the horizontal portion of AC. So Fr 3 times the distance of point 2 counterclockwise. Then I have FR2, which is at a distance of 0.3 plus 0.4, 0.7 plus 0.2, which is 0.9, but this is going to cause a clockwise rotation. So this is FR2 times 0.9. Then I have FR1 times the distance of 0.2 clockwise. Okay, then I'm going to have Cx double prime, which is going to produce a counterclockwise rotation times the distance of 0.6 meters. And then Cy double prime times the distance of 1.2 meters clockwise. And something that I always say is a point of concern. If you are struggling to calculate moments, if you're struggling between clockwise and counterclockwise, then it is time to go back to the drawing board and set those things correct. Okay, I solve for Cx double prime here, okay, because I know Cy double prime can be found out to be approximately 2850 newtons. Okay, so this is what I find out. I already know Cy double prime. Then I just sum forces in the x direction and y direction. Forces in the x direction is equal to 0. All the forces pointing to the right. What are my forces? Ax pointing to the right, Fr1 pointing to the right, Cx double prime pointing to the left. Okay, so this is going to be Ax plus Fr1 minus Cx double prime is equal to 0. Solve for Ax, 2850 minus 150. Okay, so that's essentially what I have here, and that's 2700. Okay, newtons. And lastly, sum of forces in the y direction. That's going to give me Ay. I could have done that at the beginning itself. Okay, so what are my forces? Ay pointing up, Fr3 pointing up, Fr2 pointing down, Cy double prime pointing down. So two things pointing down, two things pointing up. Okay, so this is going to be Ay plus Fr3 minus Fr2 minus Cy double prime is equal to 0. Solve for Ay, and you get this to be 1300 newtons. All these forces are obtained in the positive direction, so it means that our guess of what the direction was to begin with is correct. Okay, which is okay. I mean, if you get a negative answer, that is completely fine. Okay, it's not a big deal. So once I have Cx double prime, then I can go back, you see, to this equation here, and I can find out Cx or FDC. Okay, so I make use of that equation here. So use Cx double prime is equal to FDC minus 1000, which means that FDC is Cx double prime plus 1000. Okay, and I just want to make sure that I'm writing this properly. So Cx double prime is Cx prime minus Cx, right? So that's FDC minus 1000. Is it all taken in the proper direction? I guess I did make a mistake here. I'm very sorry. So this has to be minus Cx. Okay, so which means that this is FDC plus 1000. Not that it made a difference to our calculations for the bar AC, but I just want to make sure. So this is FDC plus 1000. I'm sorry about that. I just caught that now because I was getting some funny answers here. Okay, so this is actually going to be Cx prime double prime minus 1000. Okay, so which essentially tells me that FDC is Cx double prime, which was 2850 minus 1000, so 1850 newtons. All right, so we have actually found out all the unknowns in this problem. Okay, and so I'm now going to summarize everything for us. Okay, so in summary of the entire problem in terms of what we had to find out. Okay, the support reactions at D. Okay, if I go back to the figure for the support reactions at D, dx is the same as Cx prime, dy is equal to 0 because it's a two-force member. Okay, or DC is a two-force bar. Okay, so here I have dx is equal to FDC, which is 1850 newtons, and then dy is equal to 0. This is a 2-force member. Okay, then I look at the support reactions at A. What are the support reactions? I have AX and AY. Okay, AX was 2700 newtons and AY was 1300 newtons. Okay, this is not a two-force member. AC is not a two-force member, obviously, because you know that the distributed load acts on the bar AC. So this is the first thing I would check is if this is a frame or a truss. It obviously doesn't look like a truss at all. It has a pulley and all kinds of crazy stuff, right? So you don't want to use the principles of truss analysis here. Force exerted by the pulley on the pin at C. By the pulley on pin C. This was the force we labeled as Cx and Cy, which were both 1000 newtons. Then the force exerted by the bar DC on the pin C. This was Cx prime, which was the same as FDC, which was 1850 newtons, and then Cy prime, which is equal to 0 newtons. Okay, and then the last one, the force exerted by the bar AC on pin C. Okay, this is going to be Cx double prime, which we obtained as 2850 newtons, and then Cy double prime, which we obtained as 1000 newtons. All right, so these are the different unknowns that we have done here. Okay, so the reason for choosing those Cx primes and Cy primes, I just want to make a very quick note here. Okay, and what's the note? So the forces at pin C were initially taken to be different from each other because we don't know what the forces were at the point of beginning of the problem. Okay, the forces at pin C due to each of the three members joined or connected at the pin C were taken to be different from one another. That is Cx, Cy, Cx prime, Cy prime, Cx double prime, Cy double prime. Okay, and the reason for that is because we don't know to begin with if they are the same or not. Okay, this is because we do not know if they are the same as each other to begin with. And clearly that is not the case. As you can see, Cx double prime is not the same as Cx prime, which is not the same as Cx. Okay, so there was a good reason for our suspicion. Okay, and that's why we had to draw the pin free body diagram at C. Okay, so hence we drew the pin FBD at the point C. All right, so very quick recap of this problem. Okay, here is the main problem. I'm just going to go past a little quick. So I have bar DC, bar AC, and the pulley connected together. They are connected by means of a pin at the point C. The bar DC is supported at the wall by a pin support at D. Bar AC is supported by a pin support at A. I need to find the reaction forces, and I need to find the forces exerted on the pin C due to all of these three bars, or due to all of these three members of the frame connected together. Distributed loads are given to me as well. My strategy: get rid of the distributed load. Then inspect the frame to see if you have a chance of finding the support reactions. If not, then dismantle the frame. And the third step is, okay, do I need to draw the pin free body diagram? In this case, I have three members connected together at the pin C, the pulley, the bar DC, and the bar AC, which means I'm forced to draw the pin free body diagram. Okay, so that's typically what I do. I reduce the distributed forces to a single equivalent force, calculate what their magnitudes are, as I've done here. Then I come and look at the free body diagram, or mentally draw the free body diagram and think, hey, is it a good idea? It's not a good idea because I get four unknowns at A and D put together, but I have only three equations of equilibrium, so dismantle it completely. Once I dismantle it completely, I look at the bar AC, the bar DC, the pin, and the pulley. I need to draw the pin diagram at the pin C because there are more than two bars of the frame connected at that pin. Okay, and since that is the case, I have to assume that the forces due to each of these members of the frame are different at that pinned point. And then I make use of the idea of equilibrium of each and every piece of the frame, like we did for the method of sections, right, where we said each and every section is in a state of static equilibrium. Same idea here. Each and every part of the frame is in a state of static equilibrium. And so I make use of these calculations and I typically move on from there. Okay, draw the pin free body diagram, pulley free body diagram, bar DC, and then I come to the bar AC, and then I find out all the unknowns as I have listed down in the last page here. Alright, so I would suggest very strongly that you go back and look at this problem again, try to solve this by yourself without the aid of the solutions, and I think that will give us a good idea of how confident you are in this particular procedure. Alright, stay safe everybody, take care of yourselves. Bye bye.